Okay, here's a slight variation on a single condition ideal gas law problem. It's asking you to calculate the molar mass of an ideal gas. And so it's still going to be essentially a plug and chug situation, but we have to get to the point where we can do that. Now, recall that the molar mass of any compound is grams divided by mole. Now, we don't usually think of it as an algebraic formula, but it is. If you have some amount of mass and you know the number of moles and you divide them together, then you get the molar mass. Now, for ideal gas law problems, we don't use MOL, we use N to represent the number of moles, but it is the same thing. So if I take molar mass and represented it as G over N, then I'm starting to get a little bit of an algebraic substitution going on. If I solve that molar mass equals G over N for the number of moles, then I get the number of moles equals grams over molar mass. And that's what you do when you do a unit analysis to convert moles, grams to moles. You divide it by the molar mass. Now let's take the ideal gas law, PV equals nRT. And now notice there's N's in the ideal gas law. And so anywhere we see an N, we can replace it with G over molar mass. And so that's what I'm going to do. I'm going to rewrite the ideal gas law with the molar mass replaced, with the number of moles replaced for G over molar mass. So I get PV equals GRT over molar mass. Now I can rearrange the whole equation and solve for the molar mass. I get molar mass equals GRT over PV. Now let's take a look. I'm getting the volume, I'm getting the G, I'm getting the grams, I'm getting the pressure, and I get the temperature, and I know the gas constant. So it's essentially just still a one condition gas law problem. You just plug and chug. Now you still have to do all these the conversions. So let's convert the temperature, 100 plus 273, that's 373.15 Kelvin. Let's convert the pressure, 785 millimeters of mercury. That's 760 millimeters of mercury for 1 ATM. So I get 1.03 ATM. And I'm not going to show you the conversion between milliliters and liters. We should be able to do that pretty much with our head by now, but 650 milliliters is 0.650 liters. So let's put it all together. 1.71 grams times 373.15 Kelvin. I'm going to save that gas constant for last, divided by 1.03 ATM divided by 0.6500 liters. And now here comes my gas constant, 0.08206 liters times atmospheres over mole times Kelvin. Let's take a look. Atmospheres cancels with atmospheres, Kelvin with Kelvin, liters with liters. And that leaves me with units of grams divided by mole. And that's what I want because that's the units of molar mass. So putting this into my calculator, I get that the molar mass is 78.2 grams per mole. And that's the final answer. Okay.